Hello, Year 12, and welcome to part 2 of kinetic theory. So first activity, I would like you to pause the video and remind yourself of the key assumptions that we use when dealing with the kinetic theory of gases. Pause the video now, remind yourself what the assumptions are. So we went through all of these last lesson, so hopefully it should be fairly easy for you to recall the key assumptions, such as the gas consists of a large number of identical molecules, meaning that statistical treatments are meaningful. All collisions between molecules and the walls of the container are perfectly elastic. So that means molecule to molecule and molecule to walls. And we know that elastic means that kinetic energy is conserved. Intermolecular forces are negligible. We can ignore them. Gravity, we can also ignore. Molecules move in straight lines and at constant speed between collisions. In other words, they obey Newton's laws of motion. Collision times are negligible compared with the time between collisions. And the volume of the gas molecules is negligible compared to that of the gas. So from last lesson, this is where we got to. We derived this equation. We said that the pressure of a gas is related to the density of the gas and the mean square speed of the gas molecules or gas particles. We use molecules and particles interchangeably. I apologize to all the chemists listening for my abuse of the terms, because obviously we are assuming that these are monoatomic gas atoms. So when I say molecules, obviously you can't have a monoatomic molecule. Just please ignore that misuse of language. I'll try and use particles. So here, obviously we can see if we increase the density or increase the mean square speed of the particles, the pressure will increase. How can we increase the mean square speed? Well, obviously we can increase the temperature, which increases the energy of the particles, the kinetic energy of the particles, which means on average the speed increases. How do we increase the density? Super easy. We chuck more molecules in there, more particles in there. We're increasing the number of moles, essentially. So we're going to develop this equation today and kind of complete the maths section of this course. So we're going to jump back to internal energy, and this is very important. So it might seem like an aside, but it's very important. Now, what were two of the assumptions of the internal energy? We assumed that the molecules have no intermolecular forces except during collisions, and we assumed that the molecules, the particles, are tiny, they're far apart, and the time between collisions is far greater than the time of collisions. So what does this mean for internal energy? Well, we know that internal energy is potential plus kinetic, but we've said there are no intermolecular forces except during collisions. So is there any potential energy? Well, no, there is no potential energy for an ideal gas. Kinetic energy is the only thing we care about. So a change in energy means we are changing the kinetic energy entirely and not the potential energy. The information here is summarized, so you can make some notes. Pause the video now and make a note of this. This might seem contradictory at first because there surely must be potential energy. If we're adding energy to a liquid and turning it into a gas, well, we are increasing the potential energy, we're increasing the separation. And that's true, that's not, of course that's true. We have increased its potential energy compared to a liquid. But when we are purely dealing with a gas and modeling a gas, we make this assumption to simplify everything. And we say that any further increase of energy to that gas must purely go into the kinetic energy. So the distribution of kinetic energy follows this graph here. And you might recognize this graph from last lesson, also known as the Maxwell-Boltzmann distribution. And the number of molecules at any given energy increases rapidly until we get to the most probable, or the mode and then it decreases slowly, and we get the mean here. Okay, and it is of course interesting to note that the majority of particles that are low energy, but there are always a few particles at an extremely high energy moving with a very, very high speed. If you want to kind of see this in action, go on to PHET, P-H-E-T, and you look at the simulation that I showed you in previous lessons, or just find any kind of good animation of gas particles, and you will see that most are moving, with a relatively fixed range of speeds. Occasionally, you'll see one or two that are virtually stationary, and occasionally, because of their collisions, you'll see one or two move at an extremely high speed, but the vast majority of them are kind of here. So what now happens if we increase the temperature? Have a little think how that distribution might change. So this is what happens. Obviously, the energies increase, okay? But more interestingly, the number of molecules at a given energy actually decrease. Also, the number of molecules at a with the most sorry, I've not explained as well. The mode obviously decreases. This is the mode, it decreases, and the whole distribution is spread out. So we are obviously increasing the average, but we are also giving more particles a bit of energy rather than just shifting everything up. I'm not sure how well I've explained that. It's probably easier to just think about this graph yourself and just think about what is actually happening, the changes. If we increase this even further, make it even hotter, it continues to spread out. So this will be even hotter here. And then again, if we make it even hotter, it spreads out even further. Can we delete this? There we go. So as a little brief aside, what does this mean for chemical reactions? Well, from GCSE, you'll have talked about activation energy, and you'll know that molecules need a certain amount of energy to undergo chemical reactions, and that increasing the temperature increases the likelihood of chemical reactions happening. And you can actually see from this kind of graph how much of an effect temperature has. There we go. How much of an effect temperature has, because for a change in temperature, we massively increase the number of particles that have a given energy. It doesn't particularly matter what this energy is. It could be down here, but we're massively increasing that for a change in temperature, which is why temperature increases the rate of chemical reactions so well. So now we're going to move on to the final piece of maths. And like last lesson, the best way to understand this is to pause the video during each slide, write out the derivation for yourself, and really understand it. You might even need to do it twice. All right. If you try and skip ahead and do this too quickly, you won't really be able to follow it. You won't quite understand what's going on, and you're more likely to be confused. Take your time, do it yourself, and it'll be super easy. And just like last lesson, they are perfectly entitled, and they do ask you to reproduce certain parts of this maths in an exam. They're unlikely to get you to do the whole thing start to finish, but little bits of it, or fill in a step or rearrange and show that questions are very, very common. So this and last lesson, it is something that you should pay attention to. It is something you should look over and memorize how to do. So just before we start, pause the video and read this information on the screen and make a note of it. Paragraph 1 is super obvious, right? There's nothing that you knew from year 7 here. If two things are at the same temperature, no energy is transferred without thermal equilibrium. That's important. Moving on from that, if something's temperature doesn't change, right, because temperature is proportional to kinetic energy, then the average kinetic energy remains constant. Right. This is basic. This is a recap, but it's really worth highlighting this because this catches people out all the time. Okay, let's go on to the maths. So from last lesson, 2 lessons ago, we had the ideal gas equation. So pressure times volume equals a number of moles times the molar gas constant for an ideal gas times by the temperature of a gas, PV equals nRT. We showed last lesson that PV equals a third nmc squared. So n was the number of molecules, number of particles, m is the mass of the gas, and c is the mean square speed. It's possible that we use c here to distinguish it from v, because we don't want two v's in the same equation. I'm not entirely sure of the reason, but that seems the most sensible one. So this is velocity or speed of the particles, but we use c instead of v. So obviously, if we compare these two equations, it must be the case that nRT equals a third mc squared. If you're not sure, pause the video for 30 seconds. It'll be fairly obvious why this is true. So now we also know what kinetic energy is. Okay, we know from GCSE half mv squared. And we're going to write it using c. So these two things are equivalent. Instead of writing v, we're going to write c, probably because we don't want to have two v's in the same equation. So c is just the velocity. You'll also know that c is the speed of light. So it's possible that c was chosen because it also represents the speed of light, although obviously clearly this has nothing to do with the speed of light. So we can rewrite our expression as this, and I'll encourage you to pause the video, substitute it in yourself, and prove that this is the case. So this equation can be tidied up. We can obviously simplify the fractions somewhat. I'd encourage you to do that now. If you do that, you can end up with this. Now, n over n here, obviously this is a poor way of writing. Right? I imagine if you tidy it up, you'll end up with this. This is obviously a very poor way of writing it, but I've chosen to write it like that because n over n is a very important number. It must, by definition, be equal to Avogadro's number. Okay, because n is the total number of molecules and little n is the number of moles. So if you're not sure why, pause the video and think this through, but it must be true. So we can replace n over n by Na. So we can end up with this as our expression. So we've got kinetic energy is 3 over 2 RT over Na. So now immediately you can see we've shown that kinetic energy is directly proportional to temperature because 3 over 2 is a constant, R is a constant, and Na is a constant as well. So kinetic energy is proportional to temperature. So all these lessons, all these years since GCSE, you've been saying that temperature is just a measure of kinetic energy. Here it now is in maths. And I think this is really amazing because it shows actually really quite how simple this is. You can write down in a very short amount of maths how temperature and kinetic energy are related. I've got one further step to do though. R over Na is simplified one more time. Right? Why would we bother having two constants in an equation if we use it all the time, or we can replace it with one constant? So we say that Boltzmann's constant is R over Na. So the value for R divided by Avogadro's constant gives us this. So K is 1.38 times 10 to the minus 23 joules per Kelvin. This is given on your formula sheet. The only thing I should say is that sometimes it's written K subscript B. So it's worth just making a note that sometimes it's written as this, because obviously B stands for Boltzmann constant. So let's put all that in our equation. So we've just simplified it a bit and we've shown that kinetic energy is 3 over 2 kT. So kinetic energy is directly proportional to temperature. All there is this little constant of 3 over 2 K. So what does the kinetic energy of a gas depend on? Only depends on the temperature, nothing else. Doesn't matter what the mass of the gas is, doesn't matter what the pressure is, the volume is, it only depends on the temperature. Now, obviously, kinetic energy is half mv squared or half mc squared, but sometimes we choose to write it as this, right? Because this is kinetic energy, it might be E subscript K, kinetic energy. One more thing actually I should point out. C here is obviously the mean square. Sorry, no, ignore me. Right, so here are the symbols defined. What I was going to say before is that C is the mean square speed, but it's not because it's C squared. So we've got rid of our negative values. So the fact that things might be moving with positive and negative velocities doesn't matter because we're squaring it. Okay, a little bit beyond A level. In fact, at university, you'll see this formulation here. You won't see 3/2 kT, you'll see n/2 kT. And if you look in certain textbooks or Wikipedia, you might come across this. The reason you'll see it as n/2 is because we're not always working with monoatomic gases. If it's a monoatomic gas, then it is 3/2. But technically, it's n/2, where n is the degrees of freedom. So to understand what I mean by degrees of freedom, you've got to think about how can molecules, how can particles move. So for a monoatomic gas, how can it move? How can it store kinetic energy? Well, it can move up. It can in the y direction. It can move right or left in the x direction, and forwards or back in the z direction. So it's got 3 degrees of freedom, 3 ways of moving, which means n becomes 3. If it's a diatomic gas, well, now it's got 2 additional ways of moving. It can obviously move up, right, forwards, and back, but it can also rotate this way, and it can also rotate into the page. So it can rotate in the ZY plane, okay, which means it can store rotational energy in 2 ways as well. So when we increase its energy, as well as moving faster, up, right, left, or down, it can also rotate faster in 2 possible directions, which means n here would become 5, all right, representing that it can store more energy. Finally, if we have a non-linear molecule, it actually has 6 degrees of freedom. It can move up, right, forwards, and back. 3, it can rotate in the XY plane. It can rotate in the ZY plane, but it can also rotate one more time in the in the YZ plane. So it will actually, you can imagine this bottom one coming out of the page and going around. If you imagine this here is the axis of rotation. So it can rotate in 3 different ways, as well as moving translationally 3 different ways. And so it has 6 degrees of freedom. None of this is A level. You only need to remember the 3/2 kT. But it's just interesting to know. So in summary, the crystal kinetic energy of an ideal gas, all right, and that's equivalent to internal energy because we've ignored the potential energy, we've assumed it's 0, is 3/2 nRT. The mean kinetic energy of a molecule of ideal gas is given by 3/2 kT. What's the difference? Well, this is a single molecule. This is the entire gas. So obviously, we take a single molecule and we replace it with the constants for all of the gas molecules. Remember that K is just R/N. Okay, so if we replace K by Rn, we get to this equation here. And of course, from last lesson, pressure is the third rho C squared bar, where C squared bar is the mean square speed. So I've summarized it here again. I think this is probably a bit clearer. Right, there are 2 forms of the ideal gas equation. All right. PV equals little n RT. This is for large amounts of gas, number of moles, molar gas constant. PV equals big N KT or big N KBT. This is when we consider a small number of particles. I mean, small is relative. It can still be a very large number, but where we actually consider the number of particles. So big N is the number of particles, and K is the Boltzmann's constant. So you should be very happy to define all the symbols, and you should be able to do question number 2. So pause the video now and do these. Fairly simple. Here is all the symbols defined. Here is exactly what they mean. So it's just a case of substituting in the numbers and the units and getting an equivalent answer out. So we're going to look at 2 example questions now. Now I've slightly messed up the animations here. So we'll go backwards from this. But the mean speed of a helium atom at a temperature of 0 degrees Celsius is 1.3 kilometers per second. What is the mean speed of helium atoms on the surface of a star when the temperature is 10,000 Kelvin? Pause the video now and try this question. Okay, please excuse the fact that I've messed up the animations. I'll have to show you all the steps at the same time. So we know that the mean kinetic energy of an atom is proportional to its temperature, or absolute temperature. So this means temperature in Kelvin, because Kelvin is an absolute scale. So we know that this is true, or rearranging, we know that this is true. The mass is constant, so the mass we can cancel out, or we can just ignore because it's constant, so the 2 in the end disappear. So velocity is proportional to the square root of the temperature. We know what the first temperature is in Kelvin, simple conversion factor. We know how much it's increasing, so the temperature is increasing by this factor, 10,000 Kelvin from 273. Therefore, the speed will increase by the same factor, which is 6.05. So then just substituting in all the numbers, you get that speed is equivalent to this. You could obviously give it in meters per second in standard form, that's fine. But it's such a big number. Now, you might have solved this very slightly differently. You might have actually done a ratio V1 over V2 is square root of T over square root of T2. Absolutely fine. It's exactly the same method, just presented slightly different. Okay, we're going to do one more example question. The mean kinetic energy of a gas molecule at an absolute temperature T is given by this equation, where R is the molar gas constant and Na is the Avogadro constant. Pause the video now and try these 3 questions. So the mean kinetic energy is, of course, given by this equation here. So plug in all the numbers and you get this number here. So that, of course, was the mean kinetic energy of gas atoms. So an individual atom has a ridiculously small amount of kinetic energy. But obviously, there are so many molecules that on the whole, a gas can have quite a lot of kinetic energy. Now, what was part B? Part B said, what's the speed of carbon dioxide molecules? So we know what kinetic energy is equivalent to. So if we know what the kinetic energy of one molecule is, we can work out its velocity. We, of course, need to work out what m is, what the mass of one molecule is. So that's given by this line here. So the total mass of the atoms divided by the number of atoms in 1 mole will give us this per molecule. And if you're not entirely sure whether this is true, think back to your GCSE chemistry. Plug in all the numbers and you get 390 meters per second, which is a huge velocity. Even at 0 degrees, it's a ridiculously high velocity. So each second, you are being hit by oxygen, carbon dioxide, nitrogen molecules moving even faster than this because we're not at 0 degrees. But of course, we're used to it, so we don't notice the fact that we're being hit by something moving at a ridiculous speed. All right, and then finally, what is the change in internal energy when 1 mole of carbon dioxide gas increases its temperature? So the total kinetic energy of 1 mole of gas is obviously the kinetic energy times by the number of molecules in 1 mole, gives us this. The change in internal energy is almost entirely, or it is in this case, equivalent to the change in kinetic energy because we ignore potential energy. So simply a case of plugging in the numbers with the change in temperature here, and then we therefore get the change in kinetic energy. There is one final example here for you to read through in your own time. And then when you've finished reading through this example, I will set you lots of practice questions for the lesson. These types of questions are not hard at all. You can see how many of them rely on ratios. or just ultimately plugging in numbers. But they do require practice because there's quite a lot of different symbols, quite a lot of different steps. There are 2 or 3 different formulas you can pick from. So simply a case of practice. Students do really well on this section of the course once they've practiced. So don't be put off if it seems tricky at first. All right, thank you and goodbye.